Next, let's have a look at a couple of exam style modelling questions using the integrating factor technique. Okay, so obviously we've got a bit of a worded paragraph to read through carefully before we start the question, and then a differential equation that we're going to solve. Okay, so what are we working with? Population of bacteria, initial size 100, so I know that when t equals 0, p equals 100. Time is measured in hours, that's important. P is the population, obviously. Okay, so we've got two variables, P for population, T for hour, time in hours. And we've got a differential equation. We're also given one key piece of information which we can find our constant. And part A, solve the differential equation, and we're given an answer to show what the answer looks like. Okay, so let's look at our differential equation and think, first thing, it doesn't say use the integrating factor. So imagine you're in the exam and you get an equation like this. Could we separate variables on this? Well, we've actually got this p and t inside this bracket, so if I try to divide by this, I'd be stuck. I think it's going to be an integrating factor because we've essentially got three terms, haven't we? Let's write it in a form which will allow us to use the integrating factor. Remember, the ones that we've been looking at is dy by dx plus some sort of function of x times y equals another function of x. So what have we got? What would that be equivalent to? dp by dt. So instead of y, we've got p instead of x, we've got t. That would be some sort of function of t multiplied by p and some sort of function of t on the right hand side. So can we get it into that form? Okay, so if I rearrange this, I've got dp by dt minus 2p, so that'll become plus 2p and 100t. Okay, so this is now in a form that I can compare. The function of t is actually just a constant in this question, but we've got something multiplied by p, and we've got a function of t on the right hand side. Okay, so we can use the integrating factor on this. And the integrating factor is going to be e to the integral of 2, just 2. Be careful here, it's not the x, is it? Like instead of x, we're working with t, so that'd be with respect to t. Okay, so if we integrate 2 with respect to t, that would become e to 2t. So once we've found our integrating factor, let's multiply by it. We've got e to 2t dp by dt plus 2 e to 2t times by p, and that would be 100t e to 2t. Can be a little bit daunting with all the different letters when we're just getting used to the y's and the x's, but that, just be careful. Remember, it might be nice to do what I've done here and just compare that form with the variables that we're working with. You might even want to reference that, like, p is equivalent to y and t is equivalent to x moving forward. So we normally now get the derivative with respect to x, which would be the derivative with respect to t, of our integrating factor, which is e to 2t, times by y, which is going to be e to 2t times by p. Okay, and then we've got 100t e to 2t. Check. Is that the same? If you differentiate with respect to t, you will get this. Okay, and then all we've now got to do is just integrate this and find our constants, and hopefully we should end up with that answer. Okay, so we've got e to 2t p, which is equivalent to the integral of, I'm going to take the 100 outside. We're trying to integrate t e to 2t with respect to t. So how are we going to integrate this? We've got two functions multiplied together. Looks really good for a parts question, doesn't it? So u would equal, remember, if you're not sure, the late rule will help us decide what to let u equal. So we're going to let u equal t. That means this one is the derivative. I'm just going to call it v dash because then I don't have to worry about like if is it dv by dx, is it dv by dt. Like if I just call it u and v dash, then I'm obviously going to be integrating one and differentiating the other one. So u dash would be 1, v dash is e to the 2t. So remember we integrate this one, which would be 1/2 e to the 2t. And then let's use the parts formula, so e to the 2t, p would equal 100. You get the parts formula in the booklet, if you can't remember it, but it's u times by v, so that would be 1/2 t e to the 2t, minus, inside the integral are the two new things that we just found, so it's v times by du, and that would be 1/2 e to the 2t dt. So let's maybe not do too much at once. Let's just integrate this. So that'd be 1/2 t e to the 2t. Integrate with dividing, so we'd get dividing by another 2, so the times by half, so that'd be -1/4 e to the 2t. Plus a constant. You could put it in the brackets and then you get 100 times your constant. I'm just going to call it a constant on the outside and then I'll find that constant. Okay. Should we find a constant now? Yeah, I suppose we should. Maybe just expand this out first. So we've got e to the 2t, p would equal 50 t e to the 2t, minus 25 e to the 2t, plus a constant. You can call it 100 constants if you want, but it's just a constant that we're about to find. So we know that when t equals 0, p equals 100. When you substitute 0 into your exponential, don't forget you get e to the power 0, which is 1. 1 times 100. T equals 0, so that would disappear, so that becomes 0 times by some stuff. Minus 25, e to the power 0, which is 1, plus c, so I'm going to get 125 for my constant. Once you found your constant, back into the same line and work it out. E to the 2t, p, 50, t, e to the 2t minus 25, e to the 2t plus 125. Let's compare this with this. Yeah, we're there, aren't we? I suppose I'll just finish it off just to show you that last step. We're just going to divide by e to the 2t, so that would become, if we divide everything by e to the 2t, that would be 50t minus 25 plus 125, dividing by e to the 2t, it's the same as multiplying by e to the minus 2t, and then take a factor of 25 out. Write it in the same order, I suppose, just to make sure, but it would be fine, so that'll be 2t plus 5 e to the minus 2t minus 1. Good stuff. Okay. Okay, there's two follow-on questions once we've solved our differential equation. First one's relatively straightforward. The second one's quite tough. First one says find the size of the population after 24 hours. Time is measured in hours, so it's basically saying, look, t equals 24, what does p equal? And obviously, the great thing about this question is once you've solved your differential equation, this equation gives you the link between the time and the population. So if I wanted to know what the population was at a certain time, I can just substitute into this. Okay, just use your calculator, you get p equals 25. 2 lots of 24 plus 5 e to the minus 2 times 24 minus 1. And let me just check. Apparently that gives us 1,175. Now, bear in mind, it's not going to give us exactly that, it'll give us a decimal. But because we're thinking about the number of bacteria, just round it to the nearest whole number. And to the nearest whole number, we get 1,175. Okay. Part C says prove that the number of bacteria never falls below 40. Now, it took me a minute to think about this question when I first read this. what we've got to think about now is this is our link between the population and the time. And if we want to prove it never falls below 40, my first instinct was to see, well, can I look at this equation and think about what happens like as time increases? Because you can think about what was the initial amount of bacteria, well, that'll be at 100. As time changes, sometimes with exponentials, it'll, like the negative exponential, we know will disappear and it'll approach a certain value. But because we've got this term here, so as time increases, that term gets bigger. And this term here, as time increases, that one approaches 0. It's not immediately obvious to see where this 40 comes from. Okay, so what I then did was I looked on my graphical calculator and I sketched this graph. Can you see that? Possibly not the best. You essentially what you end up with, I had to adjust my viewing window, but what you end up with is if you plot the population against time, you end up with this sort of shape. Obviously we don't care about the negative time, so the population starts at 100 and then it does decrease for a period of time, but then after that it increases, and essentially as the time increases the population approaches infinity. And that's basically the reason why that is happening, is because when you look at this equation, we've got 50t plus 125 e to the minus 2t minus 25. Now as the time value increases, that term there approaches infinity, and that term there, the negative exponential, would approach 0. So eventually that one disappears and this dominates, and you end up with a population which gets really large. So how are we going to use this information to answer the question? Like, prove the number of bacteria never falls below 40. So imagine if that was 40 there. We want to prove that it never gets that low. And obviously once you realise what the graph looks like, we're thinking about this minimum point here. And hopefully if I can find this minimum point and show that the minimum is more than 40, we've answered the question. Like, we know it's never going to get below 40. Okay, so what we're going to do now is we're going to think about how we can find the minimum for this function and then show it's above 40. Okay, so we've got p equals 50t plus 125 e to the minus 2t minus 25. If I differentiate that, dp by dt would be 50 minus 250 e to the minus 2t. The stationary point, so let's set it equal to 0. I like to take it out of index form when I rearrange because I think it's easier. Rearranging this, you're going to get 250 divided by e to the 2t equals 50. Multiply up, divide. Okay, so we'd end up with 250 divided by 50 would be 5. That would be e to the 2t. We're trying to make t the subject, so take ln 5. Take ln on this side, you get 2t, so then divide by the 2. So t would equal a half ln 5. So essentially what I've done there is I've figured out where this minimum occurs at 1/2 ln 5. Is that enough though? Like, it's a proof question. I've got to be a bit more rigorous in my argument here. How do I prove it's a minimum, like, without using my graphical calculator to see what the graph looks like? Let's find the second derivative. So what's the second derivative? If I differentiate this again, that would become 500 e to the minus 2t. You can also think about that as 500 divided by e to the 2t. Now what we should know about exponentials is that there is clearly always more than 0. An exponential term is always more than 0. So we've got 500 divided by something positive, so I would then argue therefore the second derivative is greater than 0 for all values. I don't even need to sub in my value. Okay, so if the second derivative is always positive, we know therefore we've got a minimum. And you can link that back to the curvature of the graph as well, can't you? Like, what's that? It's convex, isn't it? That graph is always convex because the second derivative is always positive. Okay, so I know it's a minimum point. I know it occurs here. Let's go back to the question. Prove that the bacteria never fall below 40. So all I've now got to do is justify that the minimum value that we get is going to be more than 40. And how do we do that? Well, we've got the time. We want to get the population. Plug it back into your equation and see what we get. Hopefully something more than 40. Okay, so P would equal, I'll tell you what, I'll just make a bit more space. Okay, so by substituting this in, our time value for half ln5, you can use, obviously you're going to need to use your calculator for this because you can't work out that half ln5 in your head, but I suppose one thing to bear in mind is that sometimes we have to get exact answers, and we can do something with this term, can't we? So that there would be 125. We want the E and the ln to cancel. That would become minus ln5, so that would be 125. E of ln 5 to the power minus 1, so that's basically a fifth, because the E and the ln cancel, you get 1/5. But if we type this into our calculator, let's see what we end up with. I did it earlier and I get 40.2359. Okay, another way of doing this is if you go on to your graphical calculator on the graph option, once you've drawn this function and you've adjusted your viewing window to see where the graph is, you can do gsolve minimum, and it tells me that the minimum occurs at 40.2359, which is exactly what we wanted, the minimum value, just a bit below 40, and it happens at 0.847, which is a half of ln5. Okay, so obviously maybe write something to justify, a quick sentence to piece together everything that we've just done there, to justify that you proved that the minimum never falls below 40. Quite a challenging question, that one. Okay, example 5. We've got a raindrop falls vertically through a cloud. Initially the raindrop is at rest. Time is measured in seconds. Velocity is in meters per second. So straight away we know that when t is equal to 0, v is equal to 0. And again, you might want to try and link this back with the x's and the y's if you're more familiar. V is what's going to map onto y, and t is what we normally refer to as x. Okay, so it says solve, express v in terms of t. When we're asked that, express v in terms of t, what we're actually aiming to get is v is equal to some sort of function of t. Okay, so is this an integrating factor question? Well, we've got 3 terms. I suppose we could divide throughout to get this dv by dt on its own. So that I'm going to write that as 1 over 2 plus t, because that's going to be my coefficient of v, isn't it? And then that would equal just 10. Okay, so let's do the integrating factor. So it's going to be e to the integral of this, which is 1 over 2 plus t dt. A fraction, differentiate the bottom. If you differentiate 2 plus t, you get 1. The derivative is on top, so this is just straight away into an ln. And then that's really nice because they cancel. And we just get 2 plus t. Once you found your integrating factor, multiply by it. So we've got 2 plus t dv by dt plus v is equal to 10 lots of 2 plus t. This should hopefully be d by dt of the integrating factor, which is 2 plus t, times by y usually, times by v in this case. Check, does work. Okay, integrate both sides. Ten lots of something you could write as a multiple outside, so it's 2 plus t that we're integrating with respect to t. 2t plus t squared over 2 plus a constant. Find your constant. T equals 0, v equals 0. So if I sub 0 into both of these, 0 times by stuff would be 0. 10 times 0, 0 plus 0. So c is equal to 0 in this case. Okay. V equals a function of t, so just divide. One thing I've noticed, we could have actually rewritten, we could have integrated this in a different, could have done this as a bracket to a power, you know, because it's like 2 plus t to the power 1. I might do that, you know, because it'll make the numbers a bit easier. You don't need to do that, but if I'd have integrated this as a bracket to a power, look what would have happened. Because it's just a linear function, add 1 to your power, so that would be 2 plus t squared, divide by your new power, and divide by your coefficient, which is just 1. And then by doing that, we've got a bracket squared already, and then when I divide by the 2 plus t, that will cancel. I am going to slightly adjust that. So we've got 2 plus t times b. I'm going to integrate it as a bracket to a power, and then you get 5 lots of 2 plus t squared plus a constant. Oh, we found the constant was 0. Divide, so then v would equal 5 lots of 2 plus t, because you just divide and then one of the brackets cancels. Alright, is that the same answer in the booklet? Nope. What have I done there? Bear with me 1 second. Apologies guys, I figured that basically by me integrating it in a different way, we would have, the constant will not have cancelled for that one, so we should have got a constant, so apologies. So if we'd have done it this way, and written that as 5 lots of 2 plus t squared plus a constant, in that form, when you sub in t equals 0, v equals 0, you do get a constant, so you get 0 on that side. And that would be 2 squared, because in this form it's different, isn't it? So that would be 4 lots of 5, which would give me 20. So we end up with c being minus 20. So then when you have your constant, then you divide by this, and you get 5 lots of 2 plus t. That one cancels, but then this minus 20 is divided by 2 plus t. And that'll give us the same form in the booklet. Okay, part B says find the time at which the velocity is 21 meters per second. Now, obviously, once we've solved our differential equation, this is the link between the time and the velocity. It's actually given us the velocity, so we know v equals 21, and we want to solve to find t, so we're probably going to have to solve the quadratic here. If I sub 21 into this, and then I'm trying to solve to find t. So let's multiply by 2 plus t, so that would be 21, 2 plus t would equal 5, 2 plus t squared, minus 20. We're just working with the quadratic, okay? The video's a bit long, so let me just skip and see what we end up with. So if we expand this out, we get 5 t squared minus t minus 42, which does actually factorise. You can use your graphical calculator or quadratic formula, but you get 5t plus 14, t minus 3. T does not equal minus 14 over 5 because the time has got to be greater than 0, so t would equal 3. Okay, and just make a comment about why you can't reject that one. The very last thing on this question says criticise the model. Okay. Think about what are the limitations to this model. Like, whenever you're asked to criticise something, go back and think about the context. So we're looking at the velocity of a raindrop. It starts at rest. And if you look at this equation here, what would happen as time increases? So we can use this notation. As time tends towards infinity, Let's look at this fraction here. So as time gets bigger, we've got something really big on our denominator. So we're doing minus 20 divided by something really large, which is going to tend towards 0. So that term will tend towards 0. What about the rest of the function? Clearly, 10 is just 10, and then we've got 5t, which would tend towards infinity. So what this is basically saying that as the time increases, the velocity is going to tend towards infinity, because that term would tend towards infinity. It doesn't matter if that term tends to do. If one of our terms tends towards infinity, the velocity is going to tend towards infinity. Is that, do you think, the best model that we could use? Is that an ideal situation? I suppose we need to bring the context back in, talk about terminal velocity, but any sort of comment, use words. Don't just set it out using symbols like this. It's nice to justify your argument initially mathematically like this, but then you have to actually bring some sort of context in. So you could say, as the time increases, our model predicts that the velocity would increase indefinitely. In reality, you would expect the raindrop to approach a terminal velocity. Could even say due to air resistance or something along those lines. Okay, I'm gonna leave the last example for you to have a look at. The word solutions are on there. It's similar, just a modelling style question. Use the solutions, but obviously drop us an email if you're not sure. Hopefully that was useful, guys. Thank you.